Welcome, and thank you for joining us today for our live webinar on the topic of discomfort glare in outdoor nighttime environments. My name is Apparatus. I'm a member of the Illumination Engineering Society, Raleigh section, and the Education Committee Chairperson. Today's webinar is sponsored by the Illumination Engineering Society, Raleigh section, and the IES National section. We are in fact using the IES National Zoom room. The primary speaker will be Dr. Yulia Tukova in her rebroadcast of her IES presentation on discomfort glare for outdoor nighttime environments. The presentation will have the three panelists to give comments, offer ideas, and answer questions regarding this topic. We're delighted to have two panelists who are manufacturers and one designer. The manufacturer we have is Kevin Rode from WEEF Lighting USA, manufacturer also from Signify North America, Tim Ivanecki. And finally, we have representing designers and designer himself, Matthew Hartley, a principal at Matthew Hartley Lighting. As a reminder, this program will run for 1.5 hours, noon to 1:30. The flow of this program will be to view the pre-recorded session first for Yulia Tukova, followed by the panelist session. The topic, once again, is discomfort glare in outdoor nighttime environments.
2020, we are pleased to welcome Dr. Yulia Tukova as she presents Discomfort Glare in Outdoor Nighttime Environments. Yulia is an independent researcher whose primary research areas include glare, visual comfort, lighting quality, human perception, and high dynamic range luminance measurements. She received her PhD in architectural engineering lighting from the University of Nebraska. She is actively involved in technical and non-technical committees of the Illuminating Engineering Society, International Commission on Illumination, and the Transportation Research Board. She is the chair of the IES Emerging Professionals Committee that focuses on opportunities for new professionals and the benefits of the program to the society. Dr. Tukova holds 2 patents, authors scientific papers, and presents at conferences. She is a recipient of the Fulbright Scholarship and the Step Ahead Emerging Leader Award from the Manufacturing Institute, and was named a Future Thought Leader of the lighting industry by LD+A magazine in 2013. All of our webcast presentations are recorded and made available on our website exclusively to IES members. To become a member of the IES, visit www.ies.org or email membership@ies.org today. With that said, it is without any further ado, I am pleased to turn the floor over to Dr. Yulia Tukova.
Thank you, Shane. Welcome, everyone. Today I'm going to talk about the basics of discomfort glare, some of the research methods and challenges of studying discomfort glare, especially in outdoor nighttime environments. I will identify research gaps and future direction. Also, I will cover the demonstration that happened during the last IES Annual Conference and the current work of the Glare Committee. Eliminating visual discomfort is a critical part of ensuring comfortable visual environment. And in the most general sense, lighting is designed to enable the visual system to extract information from the visual environment. It's at the very least, it's important to ensure that the visual system can do so efficiently by, for example, providing sufficient lighting for task performance. It's important to also provide a good uniformity for particular applications. Complete uniformity is undesirable, but also too much non-uniformity also is undesirable. It's necessary to eliminate valence reflections, for example, such as from glossy paper and unwanted shadows. It's important to avoid flicker and eliminate and minimize glare. It's important to point out that there is more to create in visual environment than eliminating negative effects. So, for example, overall appearance and visual interest play an important role in how people feel in the space. Perception of comfort are also associated with feelings of well-being and aesthetics. And creating a unique architectural experience is also an important part of visual comfort. So there are a number of other factors, but this is not the topic of this talk. And so today I'm talking about glare. So glare is a condition of vision in which there is discomfort or a reduction in ability to see object. Glare can be direct, reflected, or overhead. So in case of direct glare, you can see that light is coming directly from the light source to the human eye. In reflected glare, we have glare that's reflected from a mirror-like surface, for example, and goes to the eye from the reflected surface. Overhead glare is a case of glare where overhead glare is a case when there is a light source that's not directly visible in your visual field, but it still can cause glare, such as right above your head. So different classifications of glare exist. For example, Voss suggested that 8 types of glare in his paper, but the 2 most common types of glare are disability glare and discomfort glare. And in this case, we will be talking about direct type of glare. The first type of glare is disability glare. It's also known as physiological type of glare. Basically, it reduces visibility due to light scattered in the eye. And so in this case, it produces luminous veil and reduces contrast and visual performance. So disability glare does not necessarily cause discomfort. So here you can see 2 different definitions of disability glare. They pretty much address the same thing. And one definition is by the IES, Illuminating Engineering Society. And the second definition is by the CIE, International Commission on Illumination. And abbreviation comes from the French name. So as you can see on the slide, the left graphics shows a situation without the scattered light, and so you can see the pedestrian pretty well. In the case of the right image, you see that there is additional scattered light, and that produces luminous veil that causes reduction in contrast and visual performance. And so it's really more difficult to see that pedestrian crossing the street. The mechanism behind the disability glare is well understood. The second type of glare is glare that produces discomfort without interfering with visual performance or visibility. And this is the type of glare I will be talking about today, and I will refer to it either as discomfort glare or simply glare. So when bright sources located in the visual field, people complain, kind of report a sensation of annoyance or pain. But that does not necessarily impair the visual performance. So this type of glare is considered to be psychological type of glare. One of the earlier CIE documents actually described the difference between these 2 types of glare as discomfort glare influences people, while disability glare actually influences visual performance or task performance. Discomfort glare is not well understood and its underlying cause is not known. Despite the lack of understanding the underlying cause of discomfort glare, there are a number of factors that are known to influence the glare perception from a single source. So the first factor is the luminance of the glare source. Here I kind of have a basic definition of luminance on the left-hand side of the slide, and the equation, and also the way you can measure luminance. And so the basic idea here is if one increases luminance of the light source while keeping all other factors equal, the perception of glare will increase as well. So the next factor that influences glare perception is the solid angle of the source. And you can see the definition, again, an equation of solid angle. And in the most basic sense, the graph that you see on this slide shows you the increase in relative glare effect with the increase in solid angle of the source. Again, assuming all other factors being equal. So it's important to know where the light source is located in relation to the line of sight. You might have noticed that when the light source is further away from your line of sight, it actually causes less problems from the glare standpoint. So if it gets kind of closer, then you'll experience more discomfort glare. And this manifests itself in the position of the light source in the field of view. So it can be either identified as the angle between the line of sight and the light source, as you can see on this image highlighted in orange, or it can either be identified by so-called position index. Also on this slide, I show you kind of a fun demonstration of peripheral acuity of human vision. So we only see sharply in the central part of our vision, and called fovea, and the fovea has the highest acuity. Outside of fovea, peripheral vision is actually spatially imprecise. So if you focus on the black dot at the center of the image, you will be able to see all letters equally well. So I'll give you a moment to try it out. So as you can see, the further it is from your line of sight, the larger the letters have to be. And all letters are equally readable because of their size have been scaled in proportion to your acuity. And this has to do with the density of photoreceptors in the human eye and the size of receptive fields. Something important to kind of keep in mind while looking at a subject of glare from different light sources in the periphery. So, and the fourth factor that is known to influence glare perception is background luminance. I have also the same definition of luminance you've seen a few slides back. And if the background luminance is increased, one will notice the reduction in glare perception. Again, assuming all other factors being equal. Also, I would like to emphasize here that talking about background luminance, we assume that background luminance is lower than luminance of the glare source. Because at some point, if we increase background luminance close to this glare source luminance, this background becomes glare source itself. So it's important to understand that it can go to saturation. So here we talk about contrast. So if we put these four factors that influence discomfort glare perception into a general form, general equation, this is what we're going to get. Both luminance of the light source and solid angle of the light source are located in the numerator, as you can see in this equation, which means if one of them is increased, the reported sensation of glare also increases. And you can see the background and position of the light source are, on the other hand, located in the numerator. And if either of them is increased, the perception of glare is decreased. So it helps to mitigate glare. So typically full equation should be applied because these factors interact. For example, if one lowers the mounting height of a light source, it will likely cause change in the solid angle of the source and background luminance. So it's important to apply the entire equation. So understanding these relationships between these factors actually provides some guidance on how to mitigate and in some cases avoid discomfort glare. So it's important to reduce luminance in critical directions. In some cases, it can be completed through feeding luminaires with appropriate optics or using diffusing elements. So, but you have to keep in mind that if that is done, it can result in a change of light distribution. Also, one has to use as much light as needed and not to overlight, and that's definitely going to help with light pollution in outdoor environments. Aim properly the light sources. I'm sure we've all seen situations when there is a light source that's not properly aimed, perhaps from a neighboring property, and that causes a lot of problems. Also, it is important to reduce contrast between source and the background. Typically, it's easier to achieve in interior spaces. Adding a layer of light on the walls typically not only helps with creating a more spacious room, but it also helps with contrast and glare. There are a number of research studies that investigated other factors in glare perceptions. For example, the influence of spectral power distribution on glare was studied in multiple studies in automotive lighting, outdoor lighting, and a few in indoor. There's some indication that sources with more blue content or short wavelength energy or higher correlated color temperature produce more glare. There's also some evidence that immediate surround luminance causes problem with, not causes problem, but has influence on glare sensation. And when I talk about the immediate surround luminance, I mean luminance that's immediately behind the light source. And non-uniformity also has been shown to influence glare perception, but I will discuss this in the later slides. So although these factors are significant, they are typically not included in the glare models. Compared to interior spaces, outdoor nighttime environments introduce unique challenges. So on this slide, I show you two images of beautiful locations with outdoor nighttime environments. And as you can see, they both have low background luminance, which in this case is dark sky. And they also characterized by a high contrast between lit and unlit surfaces, which especially between light sources and the sky. And there are multiple bright and small sources in the field of view, although larger self-luminous surfaces are certainly possible. So as you can see in this, these types of environments are very different from indoor spaces because they have different range of luminances in the field of view and different types of tasks that users typically perform. We can also kind of further subdivide them into different user groups. For example, we can talk about roadway lighting with higher mountain heights, and we can talk about pedestrian scale applications with lower mountain heights. Also, in the recent years, LEDs became more widespread in this and other types of environments. So LED technology allows to achieve performance that was not previously possible with legacy sources. These sources typically have high luminous efficacy, and here's just a mean number of luminous efficacy, which is 102 lumen per watt. That comes from the DOE report reported in 2018. You can kind of go at the link below and check it out and see more about performance of LEDs. But this is mean numbers, so this was tested among thousands of different products, and majority or large number of products have a number actually higher than this number. Color quality can also be high for LEDs. They have a variety of optical distributions, typically allowed to kind of more flexibility in the design due to the small size of the LED. So you can have narrow beams and all sorts of distributions. They also allow new form factors now. So using LEDs allow kind of use or create different types of luminaires for general lighting. They have long life as well and help save energy. So how bright are LEDs? It is an important question when we talk about LEDs and glare. And so first, there are different ways of measuring luminance. So the first one is a luminance meter that you might be familiar with, and you can see in the meter in the top left side of the slide. So when you look through the viewfinder, through the luminance meter, you will see a black measuring circle that averages everything inside of this circle. So on these images here in the middle of the slide, you can see this measuring circle pointed at a surface in the case of the left image, and in the case of the right image, you see it's aimed at the light source. And so everything inside of this black circle is averaged, and you get a single measurement of luminance. Now, if we try to measure luminance of a single LED chip, we will quickly find out that we're talking about a really small light source. So in this case, this white square is actually the luminous area. It's the area where the light is coming from. And it's roughly 1.4 by 1.4 millimeters. So it's very small light source. And so what happens when you actually try to aim a luminance meter at the LED, The measuring circle covers area, not only LED, but it covers excuse me, it covers the area immediately around the LED. And so the measurement becomes not reliable in this case, not to mention challenges with precision of aiming the meter in this particular case. So to measure the source, one can use a digital imaging photometer, also displayed in the middle of the left side, but those can be quite expensive. Or one can use a high dynamic range imaging technique, and it's typically done with digital single lens reflex camera. And in the past 15 or so years, the usage of HDRI technology has kind of rapidly increased, especially in lighting research, because it allows to capture very rich images with luminance information instead of doing point-by-point measurements. So the idea behind the high dynamic range imaging measurement of luminance is simply you have to capture multiple images of a scene from identical from identical position. So and the key here is that these images have various exposures, as you can see on the slide. And they're controlled by the shutter speed that controls exposure duration. So you can see that the left image is underexposed, and the right image is overexposed. And when you combine these images with so-called low dynamic range into one image, you get a high dynamic range image. And so dynamic range is typically describes the ratio between brightest and darkest pixels. And in this case, you extend the dynamic range from low to high. And after you get the high dynamic range image, you apply kind of a few corrections and calibrate it. And after you convert it into pseudocolors, you get this luminance image that has a lot of rich information. So basically, you can highlight the window in this image and find out how bright the window is. Or you can highlight the table and know how bright the table will be from this particular position. So when we capture luminance of a single LED with high dynamic range image as shown on this particular slide, we can see that a single LED can reach very high luminance. And we are talking here about millions of candelas per square meter. So as I mentioned earlier, luminance is a significant factor in glare perception. So when it is higher, we have higher potential for glare. And with more widespread usage of LEDs in outdoor nighttime environments, special attention should be given to this type of sources, and special attention should be given to eliminating glare by either proper luminaire design or lighting design methods. Because if not considered carefully, these types of systems will cause glare. Excuse me. For many decades, most discomfort glare research was done with subjective methods with human subjects, and there are different ways of how you can do that type of research. So the first method I'm showing here is called rate and scale method, and in this method, subject is shown a single light source, and basically they have to answer how much glare is caused by that single light source using one of the rating scales. So I give you two examples of rating scales on this slide. The first one is from Fisher's paper that I used in my research previously. It goes from 0, meaning no discomfort glare, to 6, intolerable glare. And the second scale is the Deborah Scale. And as you can see, lower numbers actually mean more glare than higher numbers. And this is quite counterintuitive. So even though the scale has a number of problems that were outlined in many papers, it is still one of the most commonly used scales in outdoor nighttime research. The second method is called single label or adjustment method. And in this case, the subject is also shown a single light source, but in this case, they are given a criterion. And criterion for this particular example is borderline between comfort and discomfort. And so the subjects adjust the light source using lighting controls, or maybe tells the experimenter to adjust the light source in such a way that perception from this light source is going to equal the given criterion. In this case is the BCD. Another method is the Parrot comparison method. And in this case, you have two stimuli presented to you either side by side or sequentially. And so an observer, typically in discrimination part of the Parrot comparison method, observer has to choose which light source creates more glare, the left or the right. In the case of matching Parrot comparison experiment, the subject has to adjust one source to match the sensation of the reference source. So when we talk about perceptions, it's not always easy to measure what people actually see, and we have to work with what people tell us. And if there's an ambiguity in any definition, it might cause some problems. Also, there are situations when we ask explicitly to evaluate glare in cases where glare would not be noticed otherwise. So it's very important to create a study that minimizes potential biases associated with experimental design and methods, scales and their meanings. So experimental design is very important and should follow best practices. So unfortunately, subjective responses are known to have high variability for a number of reasons. So it is highly desirable to either include a second method of using discomfort glare, or include a relevant objective measure to increase reliability of the collected data. So by objective, what I mean is some sort of physiological type of measure that's collected without any verbal input from observers. So in recent years, there has been a number of objective measures that researchers started to include in their research. For example, they started collecting pupil diameter, blinking rate, eye movements, frowning, and so on. So on this slide, I show you two examples of such measurements. The top two images show you a collection of pupil diameter, and the eye tracking device is aimed at the eye, and you can see it being highlighted on the top right image in white, and basically this highlighted area provides you a measurement of pupil diameter. And on the bottom, you can see another example of physiological type of measure called electromyographic reading, EMG, and it basically measures electrical activity of muscles around your eyes using electrodes. But at this point in time, none of these measures are established for glare measurements since the underlying cause of discomfort glare is not known. I guess it's also worth pointing out here that even if underlying reason for glare will be understood, there will always be a psychological component that influences glare. And a good example for this is a discomfort glare study in daylight discomfort glare study, where participants found less glare from a window with a view versus window without a view. And this is typically hard to account for. But nevertheless, the metric will be useful for relative comparisons. So there's definitely a need to establish a reliable metric for comparison and assessment of lighting installation. And both the IES and the CIE identify lighting quality and glare as strategic priorities. So you can go at the links at the bottom of the slide and kind of check it for yourself. There's very interesting research directions there, and including glare and much more, so you can check it out. Over the years, a number of glare metrics appeared in the literature and some lighting standards, and I'm not going to dig into these equations, but the idea behind these metrics is that by measuring or calculating some of the photometric components of these equations, you plug them in, and then you get a value that's typical on a scale, and you know how much glare a particular installation is going to cause. So here you can see metrics for a variety of applications, such as outdoor sports and area lighting, motor vehicle lighting, general lighting installations, and roadway. Also, I included the unified glare rating in this table established by the CIE and its extension for small sources. These metrics were developed for assessing glare in interior spaces, and they're widely used in Europe and other parts of the world. And so there have been a number of studies that kind of looked at extending these formulas to various applications. So I included these metrics here for comparison in outdoor nighttime environments. So also to keep in mind that this is not an exhaustive list of metrics. There are other metrics out there, such as cumulative brightness effect and visual system model, which is quite recent, and a number of other metrics. But when we look at this table with a number of different metrics, the question emerges, does any of these metrics predict glare most accurately or more accurately than others in outdoor nighttime environments? So in my past research, I was looking at answering this particular question in a lab study that simulated dark environment. So I had 47 observers doing this test. So on the right-hand side of the slide, you see the experimental installation. It was custom designed for this particular study. And subjects would come in and sit on a chair inside of the sphere with their head positioned on the chin rest that you can kind of see on this image or on side view here. And subjects would be looking directly straight ahead at fixation point at 0 degrees. So glare sources would be shown to them either at 0 degrees or at 10 degrees, and the size of the source can be controlled and the luminance of the source can be controlled. So this kind of translates into first 3 variables on the left-hand side, excuse me. And another variable that I was able to control is background luminance, and you can see the source right above the subject's head, located almost in the center of the sphere. In it, this source illuminated the inside of sphere and created different levels of the background luminance. So these 4 variables and different levels were combined into 36 experimental conditions. And for each experimental condition, subjects gave a rating on a scale from 0 to 6. Again, 0 means no glare and 6 means intolerable. The little image here at the bottom shows you the view that subjects saw when they were sitting inside of the sphere. So you can see it was dark and they were looking at the fixation point, and in this case, glare source was shown above the fixation point. And the goal of this study was basically to compare responses to the calculated metrics. So this slide shows you the result. This slide shows you the overall outline of the analysis of the study. So basically, I calculated glare for each of the 36 experimental conditions for each of the 4 metrics shown in the middle of the slide. And these calculations were correlated with the subjective ratings given by the subjects. So this is kind of general outline. So this slide shows you the results of the analysis. What you see here on the left-hand side is 36 experimental conditions on the x-axis, and you can decode each condition by looking at the legend at the bottom. So in the case of condition 1, you have background luminance at 0.03 candelas per square meter, solid angle at 10 to the negative 5 steradian, and so on. So you can kind of decode any experimental condition and see the results. The black curve shows the average subjective responses in this study, and the green curve shows you the UGR small source extension calculations for each of the experimental conditions. So if you look at the table of the results, you can see that UGR small source extension had the highest correlation with subjective responses in the range of conditions of the study. And the second best was a metric developed by Bullo and colleagues. So even though UGR small source extension was developed for interiors, it predicted glare most accurately in this particular study. So it's important to point out that more field studies are needed for understanding more regarding relative assessment of glare and the meanings of scale labels. But also one of the important parameters common for LEDs is non-uniformity. And this study was not designed to investigate this question. So here's an example of a source with a non-uniform luminance distribution within its aperture. So there are many parameters that can control non-uniformity, and basically non-uniformity can be achieved in many different ways. And so you can see here all the different variables that can be changed, that will change the non-uniformity. So for example, maximum luminance of this bright spot can be increased, and if we increase this luminance, it basically makes the non-uniformity go up. If we change distance between the bright light spots, they also will change the non-uniformity. And so this this type of luminary distribution or luminary design is typical for very common for LEDs. So it is generally agreed that glare from a single source is influenced by 4 variables that I talked about earlier, and they're displayed on the slide again. And they shown here, and they are part of the UGR formula that was established by the CIA in 1995 for assessment of interior spaces. And so one of the main limitations of this formula is that it doesn't take into account non-uniformity of light sources that I just talked about. So the luminance that you see in the equation in the numerator is average luminance of the light source, and so it's just one single number. But the recent studies actually showed that for the same average luminance, there is a significant difference in glare perception between uniform and non-uniform sources. And even though interpretation of non-uniformity of this study is different from one another, most agree that non-uniform sources are more discomforting when the average luminance and glare area are kept constant. So CIA committee published a technical report last year that actually addresses this problem of non-uniformity for indoor application. So on this slide, what you see again is the UGR formula, exactly the same as you've seen on the previous slide. And on the right-hand side, you see a correction of the UGR proposed by the CIA committee. So if you inspect these 2 formulas carefully, you will see that the difference between them is only in one parameter, and that's parameter K, so-called uniformity correction parameter. So in order for you to calculate the uniformity correction parameter, you need to have 4 pieces of information. So one is effective luminance of the light source, another one is effective solid angle, and another 2 is light source luminance and solid angle. So this bottom, the 2 from in the denominator are the same as in general UGR equation. So they calculated in the same way as in UGR. Effective luminance and effective solid angle is calculated in the following way. So in order to calculate them, the first thing you need to do is to capture high-resolution luminance images And as we know, luminance actually depends on the direction. And ideally, or technically, we need images from all possible directions when we talk about luminance. But it would not be very practical to take many luminance images from all possible directions. So the CIE proposes two angles from which the luminance measurements should be captured. And then the worst case scenario is chosen for the calculation. So after you capture the high luminance images, the next step is you filter the image. You apply the filter that corrects for high resolution, and that filter accounts for luminance variation that will not be seen by the human eye. After that, you remove pixels below luminance threshold, which in this case is 500 candelas per square meter. Then you calculate total area and average luminance of pixels, and then you group them into effective area and effective luminance. So then you can basically calculate correction of UGR for interior type of spaces. So what about outdoor nighttime environments? So IES does not have a published recommendation for a reliable glare metric for these types of applications. And to change the situation, a glare committee, DGONE committee, was formed. The goal of the DGONE committee is to evaluate past research and to create a technical memorandum that will allow designers and everybody else to predict, evaluate, and measure discomfort glare. And of course, there is interest in small sources in outdoor nighttime environments, especially when we talk about high mountain heights and kind of long distances. But there's a special interest also in LEDs and non-uniformity. As a part of its research efforts, the committee organized a glare demonstration at the IES Annual Conference last year. It was a truly unique opportunity for conference attendees to kind of experience complexity of research study, and I believe that more conferences should actually have these types of demonstrations and pilot studies. It emphasizes the importance of glare research and kind of allows attendees to see glare and types of problems related to glare that researchers are thinking about and designers have to consider. And also, we wanted to explore non-uniformity within the luminaires aperture in these types of environments so that it can inform future research of the committee. So the development of the glare demo apparatus took 8 months or so leading up to the conference. And there were 7 Moscow sports lighting employees working on this apparatus led by Brett Slesselman. So the apparatus structure was custom fabricated, and there was specialized lighting control software that allowed to control the conditions. And as with many research installations, it went through multiple iterations to arrive at the final design. So on the left-hand side, you see the image of a kind of construction of the apparatus back in the lab. And on the right, you see the installation of the apparatus in the conference room at the IES Annual Conference. So one of the key components of the experimental installation is the design of the source, because this is what observers are assessing. So you might ask, why to create a custom source and not to take one from the shelf? Well, custom design was necessary to create a light source with highly controlled parameters so that they can be adjusted for research purposes, in this case for non-uniformity. So in the early design, perforated sheet metal was used, as you can see on the left side, but this design didn't work well because light from the openings was illuminating the areas between the openings. And so this was not desirable. So in the final design, solid sheet metal of aluminum was used to create masks along with various diffusers. And so you can see these final designs of the masks with different openings and using different diffusers. These types of masks were fitted on the luminaire that's shown on the right-hand side, and each luminaire had about 228 high-output LEDs. So the top mask, you can see it has 4 openings. Maybe it's a little bit hard to see, but there are very small 4 openings in this mask. And in order to create the necessary level of luminance, 3D printed light pipe guide was used on the luminaire, and then it was fitted with this mask to create the final product. So we arrived at 5 final stimuli that we used at the glare demo. So this slide shows you kind of graphical representation of 5 stimuli. So the first 4 sources had equal average luminance and equal luminous flux and luminous intensity. And the difference between these 4 sources was the distribution of luminance across the aperture. So you can see 2 numbers below each light source. The first number shows you average luminance of the aperture. So as you can see, this number is the same, 6,000 candelas per square meter for all of these 4 light sources. And the second number is luminance of the luminous area. It's the area that's kind of the brightest area within the light source, higher than 500 candelas per square meter. And in the case of source number 1, you see these 2 numbers are the same because the area is the same. But for example, in source number 2, we see that luminous area is smaller, and this smaller area has higher luminance. Again, but the average luminance is the same for the first 4. Source 5 was included as a control source, and that's exactly the same as source number 1, except that the average luminance of source 5 was higher than source number 1. And we were expecting higher glare from source 5 as compared to source 1. So this photo shows you an experimental setup installed in a conference room during the IES Annual Conference. And as you can see here, there are 2 luminaires that were shown to subjects. They were shown side by side. And they had slide-in masks. The masks I showed you a few slides back. Masks were manually installed between experimental conditions, depending on which condition we were testing. The distance to the light sources was about 2.7 meters, which is roughly 8.9 feet. And we had control over the luminaires by using lighting controls. And the subjects had to look at the fixation point below light sources. And we have 2 fixation points for different days. So on day 1, we had 25 degrees below light sources, and on day 2 we had 10 degrees below light sources. So this geometry was used simply because we could not mount luminaires in any other way in a conference room, and so they had to be positioned on the same level as the eye level of the observers. These luminaires were really high, really heavy. They had really heavy heat sinks and additional fans to dissipate heat, and so they had to be positioned in the same level as the eye level. And so subjects were looking below light sources, the fixation point, to simulate real conditions. So we had black fabric on the floor and curtain to create dark environment, and overhead lighting was switched off during the test. We also had 3 subjects at a time that were participating in the experiment, and their heads were positioned on the chin rest. As you can see, there are 3 tripods with chin rests. Shield was used between experimental conditions, and so that subjects cannot see what happens between experimental conditions. And on the right-hand side, you see the actual test in progress here. And I'm glad to report that no one was harmed in the process. So this is the overall procedure, the way it was done at the conference. So we had 6 people come in a room at the same time, and they were given an observer form displayed on the right-hand side of the slide. And they had to fill out basic demographics information such as gender, age, and so on. So this also kind of gave them a few minutes to adapt to dark environment in comparison to conference rooms at the conference. So 3 observers were making assessments at the same time, and after the shielding screen was lowered, they had to look directly at the fixation point and never at the light sources. And 2 light sources were demonstrated to them side by side. Observers had to answer a question about glare for each of the 10 experimental conditions. So basically this is the view from the observer's perspective. Two sources shown to the observer side by side, and this method is called paired comparison discrimination. One of the methods I talked about earlier when I talked about ways of studying glare. And subjects were looking at the fixation point below light sources, and all they have to do is to answer which stimulus is more discomforting, the left or the right. The glare demonstration created a lot of interest during the conference. We had sold-out participation for both days, and actually not everybody could participate because all time slots were filled up. So on day 1 we had 48 subjects. On day 2 we had 54. But unfortunately data from some subjects had to be excluded. For example, as I mentioned before, it was important to look at the fixation point and not directly at the light sources because it would change the adaptation. So if we noticed that subjects were looking at the light source, we would put a note on the form and we would have to exclude the data from that particular subject. Also, in some other cases, some observers could not really decide between 2 stimuli, as shown in the example below. They would mark both left and right source as kind of equally discomforting. But in this case, they had to make the forced choice comparison. They had to choose left or right, and so if they didn't do it, their data also had to be excluded. So this slide summarizes data from both days. Day 1 on the left, where the fixation point was 25 degrees below light sources, and day 2, when the fixation point was 10 degrees below light sources. And as you can see, so the higher the percentage votes, the more glare that source causes. So you can see that source number 5 causes the most glare as compared to all other sources. And this is something that we expected, especially in comparison to source number 1, because they were equal except the average luminance of the source. So the reason I have source 4 formatted differently is because after the first day we found a problem with source number 4, as it frequently happens with pilot studies. So it was not possible to pinpoint when the problem, the issue has occurred, so the data must be interpreted with caution. So data analysis showed that there was no significant difference between any pairs of sources 1 through 4. Basically what this means is that non-uniformity did not influence glare ratings for these particular experimental conditions. And the second finding, as expected, is that each source 1 through 4 is significantly different to source 5. That means that source 5 with the highest average luminance creates the most glare. So even though non-uniformity was not significant in this particular demonstration, it is very important experience that the Glare committee is going to consider to refine the variables and identify the next research steps. So for example, the viewing angles in this demo were 25 and 10 degrees below the light sources. So it's worth exploring at which angles non-uniformity might become significant in outdoor nighttime environments. Maybe we're talking about situations with a direct viewing of the source, which is pretty common among pedestrians who are free to look around and including looking directly at the glare source. Also, it's important to point out that many aspects of this study would be done differently in a proper research environment. In the interest of time, procedure was simplified. We did not check vision of the observers. We did not do warm-up trials or did not have sufficient adaptation time. There was no control over background luminance in the conference room setup. And ideally, we would have some sort of verification of the apparatus. So it would be useful to measure, for example, illuminance at the eye at the moment when subjects give their rating. So this ensures that apparatus is working properly and they see what they're supposed to see, what they have to see. So it is also desirable to have one person at a time, so there's no potential for being influenced by someone's comments or answers, although group research settings are also possible. And to eliminate possible biases, we need to fully randomize presented conditions. So the current work of the IES DGONE committee kind of has two major tasks. So the first task is to propose a discomfort glare metric based on available knowledge. And currently the committee is divided into three task groups. Pedestrian scale, parking lots and roadway, and high mast and sports lighting. One of the main differences between these types of application is mounting height of the luminaire in different visual tasks. So again, for example, in pedestrian scale, we're talking about pedestrians looking around, and in some cases, they look directly at the light source. And in the case of like roadway lighting, drivers look mostly in a fixed point or fixed direction, and the luminaires are typically mounted higher than, for example, in pedestrian scale applications. The second major task of the committee is to conduct additional research to fill in the gaps and advance knowledge. And non-uniformity that was assessed during the Glare demo is definitely one of the research topics of interest, among other things. So our committee is definitely going to consider and look more into this topic. And to summarize, so Glare demo had created a lot of interest, which means a lot of people find this problem important to address. So the demo resulted in the apparatus that can be used and will be used for future research done by the committee. And this experience of Glare demo findings will be used to identify the next research steps. Since the IES does not have a recommendation for metric, the committee is going to propose a metric to be published in the IES standard, although it's unlikely that this metric will address all issues. However, it will address important need based on current available knowledge. And understanding the underlying reason for glare is also important.
Hopefully you enjoyed that presentation. I would like to take a few moments now to introduce the panelists that we have. I think the panelists are back on as well. So first we have Kevin Rose, VP of Sales at WEEF Lighting USA. Kevin Rose is has done a lot of exterior lighting and has been in that business for about 15 years in North America, Australia, and Asia regions. He is the specialist for exterior lighting and has worked on such iconic structures as Sydney Opera House, the Met in New York, and countless other installations. Kevin's going to bring us some great perspective from the manufacturers and design across multiple countries as it pertains to glare control. And Kevin lives in Colorado. We also have with us Tim Ivanecki. He is from Outdoor Signify North America, formerly known as Philips. I think everybody knows that. His role is to support all types of brands, Genlight outdoor brand in the Signify professional luminaires portfolio. He's got Guardco, Hadco, Lumtech, Stoneco. Tim has been lighting in lighting his whole career. And his focus for the past 25 years, does everybody hear me okay? Yep. For the past 25 years has been with brands such as Lumec and Cooper Lighting Streetworks. And Tim is in Georgia. And then finally, we have Matthew. And Matthew was formerly on the IES Street and Area Lighting Conference committees. If anybody's done anything with those committees, you've seen Matthew many times. And he is principal at Matthew Hartley Lighting. He has an architectural engineering background from the University of Colorado, and he will be giving us the designer perspective. He's worked in all kinds of areas with the IES Street and Area Lighting Committee. And he's worked on many projects, especially with exterior lighting applications in Lithonia lighting. Each panelist are going to give us about 3 to 4 minutes to present their thoughts and the key aspects from Dr. Tukhova's presentation regarding discomfort glare for outdoor lighting environments. And Matthew will go first, followed by Tim and Kevin.
Thank you again for having me. And just some of my takeaways from the presentation from a designer aspect is that, you know, we need to have this in our designs. And when we're talking about exterior lighting, we talk about sports lighting, we're talking about area lighting, roadway, and pedestrian scale lighting. And each application has its own needs for control of glare. And seeing that, having a lot of comparisons between UGR and then also the studies that were done at the annual conference, which I could say I was involved with. Hopefully I wasn't one that was actually discarded. Anyways, it's important. And we've been chasing this for a long time as an ambiguous kind of metric. And having the research being promoted and being moving forward and looking at the different metrics that are coming up and different studies, I think is exciting. I think that you know, what was done at the IES is a good demo. I agree that some of the variables need to be controlled a little bit more, but when it comes down to it, really from a designer aspect, we don't necessarily look at the manufacturing side of how it's all put together. We need to have the tools when we do our designs to be able to show, you know, what might be discomfort, what might be discomfort glare. And with this, I always caution it that with UGR, anything with UGR, make sure it's in situ with a design and not a single fixture. Since that does affect how it's interpreted, because like I said, each scenario is different. And then also for what's coming out, you know, if it is discovered that the non-uniform sources might be an issue, that needs to be worked into the data that comes out of the manufacturers. But we just need tools to interpret this and to be able to make a more comfortable environment. And I've done designs and been and I visited my designs and visited other designs where we take into account the glare, and it makes a space much more enjoyable when you don't have that discomfort glare. So I'll leave that and turn it over to Tim.
Thanks, Matt. You covered a lot of ground. You know, as a large manufacturer, we've certainly heard in the marketplace, the need for better glare control for in the outdoor environment. You know, with LED bursting on the scene, you know, how many years ago, and you know, at that point, you know, it was the be all end all, and now we're with the source becoming so much more efficient, and mounting heights dropping and design light levels not dropping, it has really created quite a stir in the marketplace, and quite frankly, I mean, it's what drives a lot of the lighting ordinances that all of us have to deal with on an ongoing basis. So we've certainly heard, and we're trying a lot of different things right now to try and come up with better working solutions, quite frankly, because again, you know, being a big boy in the industry, we know we need to take a leadership position and try and come up with solutions that designers want to use, quite frankly, and that in itself raises plenty of challenges there, because it's everybody at this point has their ideas of what those solutions should be. So it does provide some challenges. But again, I mean, we've taken some steps to come up with some current solutions, as well as I know we've got ongoing efforts to come up with others, really focusing on the what I'll call the mid height and below, focusing of course a lot on the pedestrian scale applications, because that's a big part of the market that we serve. And with that, I'll turn it over to Kevin. Let him say his piece.
Thanks, Tim. I have to tell you, I had to watch that presentation probably 4 or 5 times to really take it in. All right, so it's and I think the work is really important. And it was encouraging for me as we're a little boy in the industry. You know, Tim, you work for one of the big boys in the industry, but you know, WEF is a relatively small specialist in exterior lighting, and you know, we may cover many parts of the world, but you know, we see ourselves as a performance lighting company. All right, so we really focus on things like optics, for example, and what we come across the most, or certainly what I've come across the most, is like, you know, when I get this question of glare, is how do we factor it in? Because from our point of view, a lot of that is up to the designer, you know, and it can be a simple solution as dimming, you know, as simply dimming the luminaire to reduce the intensity of the light of the light sources. It can be as simple as using more luminaires. You know, put my sales hat on and say, buy more luminaires. But you know, the commoditization of luminaires, you know, I certainly see, and having worked in other countries, what I've certainly seen in North America is this desire for cost reduction, which often means poles get higher, luminaires get brighter, and control goes out the door. And even when I look at things like the DLC, the Design Light Consortium, you know, the efficiencies that they're pushing for right now is almost suggesting, you know, to my little lighting designer's head, that optics aren't important. It's more about efficiency. All right, so we have all these forces in the market, which I think play against the desire to reduce glare. And I've got to say one thing, coming from my time in Australia, and one of the things which I've noticed, you know, coming to the USA in particular, one of the things that drove almost all of the lighting designs that we did in that market was vertical illuminance. All right, so we always did our measurements at sort of like 1.5 meters above the grade, and the measurements were always taken in 2 directions. All right, and the concept there is okay. You do need you cannot now light a car park from the center. All right, because if you light the car park from the center, you know, God forbid you're walking to your vehicle, this person's approaching you with a baseball bat in their hand, and all you see is a silhouette. All right, so more light, more luminaires, less light, and dimming for us, you know, is one thing that just, from my point of view, the customer just seems to forget. I could sit here and rant on forever. The other one the other point I'll make is that, from a manufacturer's point of view, I remember slide 42 of her presentation where she says that, the non-uniformity is not necessarily an influence on the glare rating. And that's really comforting from a luminaire manufacturer like ourselves, which does, focuses on small, optics like this across large panels. And, you saw that in the example. Because to move away from that sort of design to a design where perhaps you don't see the light source, and I do often get the request, I don't want to see the diode. I don't want to see the diode. It's glary. It's actually not glary. It's glary when the light source is focused and directed towards your eye. But I do see confusion and subjectivity around this whole idea of what is glare. Sometimes if someone just sees light, it's glary. So that's the sort of things that we have trouble with as a manufacturer. Often it does just get back to the designer. We obviously are under some financial pressure and design considerations. We have to consider thermal management. We obviously have to consider the availability of the LEDs that we want to use, and also the design requirements of the space. So it's more than just glare from a manufacturer's point of view. So from my point of view, I would push it back onto the designer and say to them, first of all, be very clear what you want, and don't be afraid to make that extra step to include glare control as part of your design consideration, because so often I see the economics of an installation getting in the way. So that's my rant.
Yep, good, Kevin. That is excellent because it leads right into a very good question. We've got basically 15 minutes for a bunch of questions, but here's one from the panelists, which I really like, which is, while we await IES guidance for glare metrics, do the panelists recommend a particular technique that the designers can apply right now in an attempt to mitigate discomfort glare? And we'll just go around again. So we'll start alphabetically. So it'll be Matthew first telling us, and then we go to Tim, and then to Kevin. And hopefully we can get another question in as well. So go for it, Matthew.
So definitely there's some techniques that you could use, and I could talk about from the practical standpoint. CIE had done a lot of research. Obviously, you saw a lot of CIE documents referenced in the presentation. One that I've used is the GR for area lighting, but there are drawbacks to each of these, and you have to keep in mind a lot of these metrics were designed pre-LED. And so we're getting brighter sources. We're getting, as we talked about, the sources get brighter, the mounting heights, but it also comes down to design technique. And again, what you're trying to light. In a lot of cases, when you're doing a parking lot, you want to make sure that the glare source is somewhat located outside your field of view, and the amount of light that you have is lower, because as she mentioned in the presentation, you have that solid angle and you have the luminance from that fixture. When you decrease that solid angle but maintain that luminance, it can affect your design. So it comes down to really a lot of practical knowledge. But if you had to use a metric, I use glare rating for a lot of my exterior designs in that case, because it does meet that. It is defensible, I guess, is a good way to put it.
I am not a lighting designer. So, I mean, as far as a metric goes, I mean, right now, that's been really the big question, is we don't really have, and that's something that Yulia brought up, is we don't have a good metric right now that could be uniformly applied. And that's really the crux of the whole discussion, really. But so much of this starts and really stops really with the design criteria. We have a real big tendency to overlight everything. And when you overlight at your base grade, it makes it very hard to create a visual interest with your accent. And consequently, it snowballs downhill real quick. So really, I think we need to focus on bringing our light levels down, and then ideally adapting light for activity, so that if we don't have activity, no reason to have a whole lot of light hanging around. And I think that'll go a long way with answering a lot of questions that we have in the marketplace today.
Yeah, you're putting it on saying controls. Controls are really
controls, not only in terms of how and where we put light, but also in terms of when we light. Certainly, because it all gets connected and makes a difference.
Mm.
Kevin.
I mean, the reference I use, and I'm like you, I'm no lighting designer, but the reference I use within when I consider the glare from one of our luminaires is simply I look at the photometric file and I look at the peak candela intensity, and if it's high, I'm going to direct people towards a different luminaire, or I'm going to suggest to people to dim. And but as you just said, I think we've all agreed on it's a little bit more than that. All right. So, but yeah, for me, it's peak candela intensity and the layout and the design itself.
Good question. We have another good question here. Let's see, we got about 10 minutes. What are the best methods programs available for specifiers designers to utilize in selecting fixtures and layouts to ensure proper design to avoid potential glare issues? Is there a method for us to calculate the glare on a project similar to photometric calculation? For now.
That one's on you, buddy. I couldn't even guess.
It's a tough question. So let's think about a little bit further. Here's one that there's a glare metric. Oh, so we got another follow-up, I think. No. Okay, so I'm going to switch questions just a little bit on. So what are manufacturers thinking about for solutions for discomfort glare? And you kind of sort of answered that. You say dim, controls, lower light levels, and what is the task? What is the activity? You kind of answer that well. Here's kind of an outside question. How relevant is the bug system to mitigate glare from outdoor lighting fixtures? How relevant is the bug system?
So I'd like to start off with that one real quick, and I do have an answer to the methods programs available as well. But to answer this question first, realistically, the bug rating was developed to kind of come out with a new metric to get away from cutoff, semi-cutoff, full cutoff, non-cutoff classifications. And it was to enhance how a fixture is actually evaluated. At that time, we didn't, that's the only metric we really had, and that in CU. So it was built and it was designed to achieve that. And I think that it's a good starting point when you're doing your design to look at the bug rating and to see where it lands. Now, there are some flaws that they're going to be working on with the new revision, the TM15. However, something like, say, just throwing it out there, it doesn't deal with glare, but uplight, if you have one candela going up, it ruins your uplight rating. So that's something that keeps in mind that just with testing procedures, you might get a little bit of that, and there needs to be some variation. But in my opinion, it's a good place to start. And then you put that into your design, you put that fixture in the design and evaluate it to see exactly how the glare is functioning based off the bug rating. You also need to look at critical angles. And so it takes a little bit more of a deeper dive into the photometrics than just saying, oh, this meets this bug rating, we're good to go. But again, it's a good place to start. in my opinion.
And I would echo exact that. It's a starting place. It's not the be all end all that a lot of folks try to make it. But it certainly is well, I mean, it's the only metric, what I'll call universal metric that we have today that most designers seem to know and lean on. But again, it does have some limitations because again, quite frankly, and much to what Kevin alluded to earlier, is economics gets in between the design and the implementation. Every time we stick a pole in the ground, a pole base in the ground, we spend $3,000. So we have to build our own infrastructure in order to light the nighttime environment. Whereas that adds a lot of cost to a project, and consequently we have to be conscious and aware of how that money is spent. And that's part of the reason that the big dilemma that we find ourselves in, and trying to really find that good balancing act between, what's an acceptable peak angle, if you will, to for a luminaire, so that we don't overextend ourselves, I'll say.
Mm-hmm. So I don't know if both of you saw the follow-up question on this. Is the bug rating as relevant to LED as with HID? And maybe Kevin, you want to add that into your...
Yes, it is. Yes, it is. I think, my view on the bug rating maybe is a little bit different. And that is that I think the industry, the bug rating is great as a start, but the industry is looking for direction, in my opinion. And it leaves us with a lot of unanswered questions. I sat down when I thought about this. I was thinking, thinking about the sort of questions I've had over the years from bug rating, and I've had questions such as, can you give me the backlight number for this recessed step light? Can you give me I want to be sure that you have a U0, right, uplight of 0 on your recessed ceiling luminaire. And it's clear to me that first of all, these questions don't come from designers, right? They don't come from lighting designers. They come from people who possibly people who work for municipalities, but people who don't have an education in lighting. But we do see a lack of direction even in the industry itself. And I'll give you an example of a bollard, for example. Let's take a bollard out of Europe, and I'm not going to name names, but you'll notice that there'll be some uplight in the photometry. And what they've done in the bollard is they've actually picked up the light on the column section of the bollard, and that's creating uplight. They haven't taken it out. You then take the photometry from a US manufacturer, and through magic, there's no uplight. All right, and I can see the logic. I can see the logic. Well, why would you do that with a post stop? You don't photometer the pole in a post stop. So why would you photometer the column section of a bollard? It makes sense, but there is nothing in there to direct us, with regards to the bug rating about how we should use it, and when to use it, and also when not to use it. Because certainly I see the types of questions I get are mainly about people who don't understand when not to use it. I don't know if others have experienced the same thing.
Matthew, you have a comment on that? So
yeah, I mean, as far as LED, HID, the data is the data. When you do a photometry test, the data is the data. So it's the same. Visibility wise, when you're looking at it, it can be a little bit different. But I do think that the big thing that we need to look at is education in the industry, and education. I mean, because we're looking at like the MLO, and that's tied in with TN15, and we're saying you have to have these ratings for these areas. And when we're introducing that out, we're talking to lighting designers, and they're getting educated on what they need to design to. However, when you make it a part of a model lighting ordinance, the person, as Kevin is specified or stated, that's asking for the backlight for a step light or the uplight from a recessed ceiling exterior fixture, they obviously don't have that education, and they're just going off of, hey, this is what it says I need to have, this is what I need to do. And so we need to have, in that case, a little bit more outreach for people to understand these different aspects. And there are, like I said, there are limitations. And you have to understand, as we put out these metrics, you have to understand, and we as people who make the metrics have to know where the limitations are, and have to know where it might falter, and say, this is what we're recommending. This is a really good place. It may be perfect, might be, but it may not be. And we usually discover that down the road, and we need to educate people on that. I think education is extremely important.
Well, thank you, all of you. We got 2 minutes left on this panel, so there's not much more time to ask any deeper questions. Before I go around for one last thought, maybe 30 seconds on each thought, I would welcome all of the members to join different committees on the IES to share their knowledge, come up with new ideas, new standards perhaps for outdoor lighting. So that's just a plug back to IES to join those committees. Anyway, we'll start again, go around 30 seconds for each one of you to complete out whatever final thoughts you might have on the presentation or, future direction. So we'll go back with you, Matt.
Okay. So I guess, as I mentioned before, the best methods programs available, just say that there are different software lighting programs that have glare metrics built into them, but it does come back down to design. This is a whole relationship between the designer and the manufacturer. The manufacturer is going to make the product, and the designer has to know where to put it in and how to implement it and what the situation is. So if you're doing a park or doing something where you want to have light in the park, you're going to have a different background luminance than you will for a roadway. And so you have to understand the different aspects of the glare and try to design that. And that's where experience and education comes into play for the glare rating when you're doing those designs. So I know that we have a ways to go, and I know that there's the demonstration that they've done and some of the research that they've done has been great, but we still have more further to go. And I think we're getting there. I think we have the support to do that.
Tim?
Well, I can tell you this, as we continue to develop product and redevelop product, a lot of times we reach out to the industry for what we call our voice of customer. And that's something that would certainly reach out to feel free to reach out to if you have ideas of what you'd like to see in the way of product development. Certainly always looking for valuable market input. That I can tell you, again, and that's something that we value tremendously. Anytime we go to develop new product, we certainly are not designing it in a box and just going to throw it over the fence and say, look what we did. No, we're interested in hearing what the market wants and needs, and always hearing, what the expectations are for a like product in the marketplace, that to meet that unmet need, whether that, and if that's coming up with something that the latest greatest widget with that's glare free, hey, we'll take a stab at it. Just need to know what the requirements are, the application is, and how we can commercialize it, quite frankly.
Kevin, last thoughts?
Yeah. Look, I think Yulia's work is really important, and I do share Matt's comments. At the end of the day, it does come back to the design, because as a manufacturer, we're going to try and meet whatever the needs of our customer is. So if the need is for a high output post-op luminaire that says to hell with glare, well, we're going to do it, right? But if the more we can push back on this, the more we can promote visual comfort and the need for better glare control. Manufacturers like ourselves are going to try and meet those needs. So I I said, it's really important work, and I hope she throws that research over the pond to Europe as well, because it's, it'll be good to see those, some of these standards, some of the pressures also coming from that end of the world.
Well, thank you, everybody. Thank you, panelists. Thank you, Lynn. And thank you all members and panelists and attendees for this presentation. Feel free to reach out to any of us at any time to in this topic or other topics. And if you want to really get deeply involved in the standards, join one of the IES committees for sure and learn more and contribute. Thanks again and appreciate it, and see you next time.